Hello everybody and welcome to lesson 2, going on to continue the definitions of vectors used for electromagnetism. So I want to go through this as thoroughly as possible so that we can learn about the definitions of vectors, which are going to be fundamental to their use in electromagnetism. So we need to understand how to define them, how to manipulate them, and how to uh, take any other transformation of these vectors. So the last time we spoke, we went over the idea of components of vectors. And we defined the x hat, the y hat, and the z hat component, as well as the normal component. So the x hat, the y hat, and the z hat component are simply a vector of unit length that is pointing in either the x, y, or z direction. So from that, we were able to define the dot product as a more rigorous definition rather than AB cosine theta. We can define it as the multiplication of each of the components of vectors A and B and adding them all together, and then you get a scalar in the end. So we can do the same with the cross product, with the idea that crossing any vector with itself is equal to 0. You can only get a non-zero vector when you get a perpendicular, two vectors that are perpendicular to each other. So, looking at our book, we have the definition of cross products of vectors, of the unit vectors. And I want you to go out and show this to yourself. But again, if you take a vector cross to another vector, you simply take your fingers and point them in the direction of one vector, curl them towards the other vector, and wherever your thumb is pointed is the direction of the resulting vector. So if we're looking at unit vectors, we know that all vectors have unit length. So under the simple definition of the cross product, where it is equal to AB sine theta, we know that A and B are equal to 1. So our resulting vector is a unit length. What direction is it pointing in? Well, if we have x hat and y hat, x hat curled into y hat is equal to z hat. Y hat curled into z hat is x hat. And z hat curled into x hat is y hat. A good way to remember that is if you have x, y, z, x, y. Why is that not showing up? Okay. Okay. No. So that's unfortunate. I don't know why. It is not working. Properties, except for here we go. Okay. That was strange. So, if we have x, y, and z, if you write this little mnemonic out, you can figure out what your resulting vector is. So going from x to y gives you z. Going from y to z gives you x. And going from z to x gives you y. Now, you can go the other way as well. If you go from y to x, you get a negative z. So if you go to the left, you get negative values. So y to x is negative z, x to z is negative y, and z to y is negative x. So, handy little mnemonic there. So let's continue on to what the cross product is. So if you cross all of those terms together, you're going to have 9 terms, which are going to see. Yes, you're going to have 9 terms, 3 of which are going to drop out and turn to 0. So your final resulting expression is going to be this god-awful expression. But if you want to remember it simply, you can just remember the determinant of the vector. So the cross product of 2 vectors is equal to the determinant, where your top row is your unit vectors, and then your middle row and bottom row are your vector 1 and vector 2. I won't go over how to take the determinant of a vector. That should be known to you by now if you're taking this course in school. Also, I won't be going over any fundamental definitions of calculus. I will be going over vector calculus, but I will not define what a limit and what an integral is. I will assume that is known. So I will assume that you have some level of Calc 1, 2, and 3. So, from that, we have finished up and we've got our cross product. So, let's move on to, those were our 3 definitions of products of vectors. We had the scalar product, the dot product, and the vector product. Sorry, the cross product. Now we can have triple products. So we can have 2 of those. We can dot a vector into 2 crossed vectors, and we can cross all 3 vectors. We can't cross 2 vectors and then we can't dot 2 vectors and then cross them, because we'd be crossing a scalar with a vector, and that is not defined. So, by simply going through some of the very tedious math, but straightforward, we can define A dot B cross C, which is distributive. So, in order to preserve this, you need to make sure that you have your negative signs in the right way. So you can distribute your dot. Well, you have to do your cross product first and then get your dot. And this will be a definition that you will go through many that you will use, but can easily be looked up. One of the geometric forms of this is, like we said before, the geometric definition of a cross product is the area of a parallelogram that the two vectors create. Well, the scalar triple product is simply the volume of a parallelepiped that the three vectors create. Because the area is A cross is your B and C for this definition, and then you get the height of the parallelepiped by doing A cosine theta, which is your dot product. So you can remember A dot B cross C, and you can start to do the math, or you can just remember its components form, that A dot B cross C is simply the determinant of A, B, and C. So let's go on to the final triple product, which is the vector triple product, so A cross B cross C. And that follows what is known as the back cab rule. You can see that A cross B cross C, if you write out all of your components, so you're going to have 9 total components, AX, AY, AZ, BX, BY, BZ, CX, CY, CZ, and you cross them all together, you will get B times the quantity of A dot C minus C dot times the quantity of A dot B. BAC minus CAB, the back cab rule. So we can go into higher order definitions, but those are more esoteric. They're not really required. So let's start talking about position vectors. This is going to be very important in defining electric fields and sources and everything relative to an origin. So we are going to go over some simple definitions. So the first definition is that of the position vector, which a position vector is simply a vector going from the origin to a point in space along that direction. So it is a function of x, y, and z, and its component r is in r hat is in the direction of r. So we know our magnitude of r is simply the value of x, y, and z squared and then square rooted. And then we can define what the normal vector is. Now the normal vector is a unit vector in the direction of r, remember. So we know the direction of r because we have the vector. It's x hat, y hat, z hat. And how do we normalize it? Well, we know its magnitude. We divide by its magnitude. So simply dividing by square root. And that gives us the normal vector. We then can define the displacement vector. So x plus a tiny shift in the x direction, y plus a tiny shift in the y direction, z plus a tiny shift in the z direction gives us our infinitesimal displacement vector dl, which is just dx x hat, dy y hat, dz z hat. So we want to come to a simple definition of source points and field points, which we will get into very soon when we get into electromagnetic fields. So a source point is a point at which a source is located. So you can think of this as a clump of charge. And a field point is a point at which you want to know the quantity of the field due to the source point. So we have three vectors that define that. We have r prime, which goes from the origin to the source, r, which goes from the origin to the field, and then cursive r, which is just the source to the field point. So cursive r is just the difference between r and r prime. And we can define its magnitude, we can define the unit vector r hat, and simply in Cartesian coordinates, we have r equal to this. The magnitude here, and the unit vector r hat. So this is going to be a very important definition to remember because it's going to be used constantly. So it's simply the difference between the unprimed and primed coordinates in each of the x, y, and z directions. Simple. So how vectors transform. We can skip vector transformation and we can start getting into the differential calculus. So differential calculus gets into tiny changes of three-dimensional variables. So we can first define what a gradient is. Now, a gradient can be seen as a slope in a particular direction, but strict definition is given here. So let's back up. So if we are looking at the temperature of a room and we want to know how it's changing throughout the room, we can measure the temperature at each point in space, get a function, and we can look at how that function changes as you move in position. So the infinitesimal change in the temperature from one point to a point plus a delta x, delta y, and delta z is simply the partial derivative of the function t with respect to x, partial derivative t with respect to y, plus the partial derivative of t with respect to z, times the dx, the dy, and the dz. Partial derivatives are simply taking the derivative of a function, assuming that all other variables are held stationary. So if you have the function of f of x, y, let's just do two variables for now, then the partial derivative of f with respect to x is equal to the derivative of f of x, assuming that y is held constant. So if we had f of x is equal to x squared plus xy, then df of dx is simply going to be keep y constant. There's no y in here, so we have 2x. We add, we keep y constant, and the derivative of x times the constant is just 1. So we have y. And the partial of f with respect to y, x squared, there is no y in here, so it's going to be 0, plus derivative of y is 1, x. There we go. Very simple. We'll get into more complicated functions later, but for now, we'll stick with this. So, we want to know what the gradient is. Well, we have this dt, which looks kind of like our dot product definition. We have some quantity a times some quantity b, a times b, a times b, all added together. Well, what are a and b? Well, they have to be vectors. So our b is our little infinitesimal line segment, dx, dy, dz, in each of those three directions. And what's our a vector? Well, our a vector is defined like this, just the partial of t with respect to x in the x hat direction, plus that in the y hat, plus that in the z hat direction. And we write that as this upside down triangle, which is known as the del operator. It is an operation onto t. And we have that definition here. So this is the gradient of t. Gradient being a vector quantity. You take a scalar value and you multiply the del, you apply the del operation to it, and you get a vector. So what does that mean? Well, the gradient points in the direction of maximum increase for the function. That is our geometrical meaning. While the magnitude of the gradient gives us the rate at which that increase occurs. So you're getting a direction at where the greatest increase occurs, as well as a value of its slope. So, find the gradient of r. Very simple. Del operating onto r. So we have our del operator. We have what r is equal to. We simply take our derivative of each of this. We apply the product rule and the chain rule, mostly the chain rule, for each of the x, y, and z components. And we get 1/2 of 2x divided by the magnitude, 1/2 plus 2y over the magnitude, 1/2 plus 2z over the magnitude. Simply just the magnitude of r, the vector r, divided by the magnitude of r, which is just r hat. So, the greatest increase in r occurs in the radial direction, and it's of the unit length. Very simple. So, since there are no people here, we'll just continue on to our operation. So, I am more than happy to go over problems. They're straightforward. We can go over them together, and I want to get through as much of the lesson as possible, so I want to avoid the problems. But it is good to know that problems are very helpful in solidifying your understanding of electromagnetism. But that can be done when people interact and ask questions. So, let's see if we can get up to integral calculus. So first, we've talked about the del operator, and we've defined it. And we can multiply, it's a vector, it's an operation. It is not a vector. It needs something to be applied to, so it's an operation. That acts upon a vector. We could do multiply vectors in 3 ways, so scalar, the dot product, and the cross product. We can apply del in 3 different ways. The scalar function, which we just learned, the gradient, and then 2 new ones, which are the divergence and the curl. So del dot a vector and del cross a vector. So let's look at the divergence. Taking the products and simply dotting them into each other and then adding them together. We're going by the strict definition. We get the partial of the vector in the x direction with respect to x, partial vector the y direction with respect to y, partial of the z vector with respect to z, all added together. So, what does that mean? What does that look like? Well, the divergence measures how much a vector spreads out from a point in question. So, if we look at these figures, we can see that there's a large divergence in the positive direction, radially outward. And remember that v is a vector function. It is a function that has components in the x, y, and z direction. It will tell you where a vector is pointing at each position in space. This is the definition of fields. So, let's move on. Into the curl. So like we had before, the definition of the cross product is simply the normal components x, y, and z crossed into a determinant. Top row is components, second row is a vector, third row is b vector. So if we have del cross v, we have our x, y, z, our partial operations, and then our components in the x, y, and z direction. And we simply multiply that out, and we get our curl. Now, the curl of a vector is, like its name implies, tells you how much a vector swirls around a particular point. So the two figures here, A and B, show you how these vectors are moving around the z-axis. And you can imagine that this is zoomed in really close, and this has a source really close, and this has a source really far away. But it is perpendicular. The curl is in the z direction. Okay, so let's get into more vector calculus. So we know that the product rules of calculus, we have the sum rule, the multiplying by a constant, the product rule, and the quotient rule. So similar ones hold for vectors. So if we apply the del operator to two functions, f and g, it's the same as applying the del operator to the function f plus the del operator on the function g. Dotting into two functions a and b is simply the same as dotting a plus dotting b. Crossing onto a plus b is the same as crossing a plus crossing b. Very simple. Scalars can be pulled out of the del operation, just like normal calculus rules. Product rules are not quite so simple. Two ways to construct a scalar in a product of two functions. We can take two scalar functions and multiply them together, or we can take two vector functions and dot them together. Two ways to make a vector: scalar times a vector, or the cross product of a vector. So there are a lot of different product rules. Two for gradients, two for divergences, and two for curls. And those are defined here. So these types of products are product rules are used enough that you can just use them to look them up. Any teacher that has you memorize these is, in my opinion, wasting your time. You will remember them if you use them frequently. And from that, we can define quotient rules, which can be obtained from the product rules, but that's about it. So, let's look at second derivatives. So, we can take the del operator and apply it onto other vector and scalar products. So we can do the divergence of a gradient, del dot del t, curl of a gradient, del cross del t, and we can do the gradient of a divergence, del times del dot v. Finally, we can do divergence of a curl and the curl of a curl. None of this is groundbreaking. This, by applying the definitions, we simply have our del operations So here, the divergence of a gradient is simply the second partial derivative of the function with respect to x, y, and z added together. And short notated, we call the del squared operation, also known as the Laplacian of t. So the curl of a gradient is always 0. The divergence of a curl is always 0. And then we have del cross v is equal to the gradient of the divergence minus the Laplacian of v. This is all straightforward. And we get into integral calculus. And Stokes' theorem, curvilinear coordinates. We've got a lot to go through. Dirac delta and potentials. Okay. So we've got a lot to move through. And we've only been going for 40 minutes. Okay. So, looking to stop right here. We'll tackle integral calculus next class, and then we'll do curvilinear coordinates after that, and see if we can get to that, electrostatics, by sometime next week. So, that's it for me. I am Sci-Guy Geek. Be sure to Be sure to like and subscribe. Hope you all have a good night. Take care. If you're interested in this, check out my YouTube video, where I will be posting all of these lessons onto YouTube. So, thank you, and take care.